Good afternoon, everyone. I'm Chinjo, the chair of the Department of Statistics and Data Science at UCLA. So welcome to this special joint seminar organized by our department and the Department of Biostatistics. Today, we gather here to celebrate a truly remarkable milestone, the 50th anniversary of Professor Tom Ferguson's Dirichlet process paper. I'm extremely happy to let you know that Tom is here with us and for this special event. Thanks for coming, Tom. So this is the paper we're going to focus on today. The title is A Bayesian Analysis of Some Non-Parametric Problems. It was published in the Annals of Statistics in 1973 when Tom was a faculty member in the math department at UCLA. In this paper, Professor Tom Ferguson invented the Dirichlet process, a concept that has since become a cornerstone of Bayesian non-parametric statistics. This landmark paper paved the way for a new era in statistical modeling and inference, inspiring researchers and practitioners to explore the potential of Bayesian non-parametric methods. The journey of 50 years has seen countless advancements, applications, and innovations, all rooted in the ground laid by this paper. So in today's seminar, we will see the continued influence of the Dirichlet process on diverse fields, from mathematical statistics to many applied problems, from machine learning to data science. We will hear from leading experts and scholars in this field, shedding light on how Tom's work has shaped and will continue to shape our research community. This event is also a special component of the 25th anniversary of the Department of Statistics at UCLA, which was established in 1998. Tom was a founder of our department. Although he had already formally retired at that time, Tom continued his research, teaching, and service in our department for more than 10 years after its establishment. So at the beginning, when we had this idea to organize this event, we didn't talk to Tom because Tom was very moderate. He might say no. So when we have organized most of things, then I sent an email to Tom about this event. As always, Tom was very moderate and he replied. He said, "Dear Chin, I am honored and surprised that my 1973 paper is still of interest." So I wanted to say that the honor is really shared by all of us as we celebrate this remarkable work with Tom. And it's not surprising at all that the paper continues to generate interest as its impact will endure for many years to come. As a statistician, I admire Tom for his invaluable contributions to our research community. As a colleague, I greatly appreciate Tom's work and support to our department. Thank you, Tom. So once again, welcome everyone. So let's get started with the talks. So I'm pleased to invite my colleague, Professor Michele Guindani in biostatistics to introduce today's speakers and talks. Thank you.
Well, it is a pleasure to be here today with you and the three prominent speakers for this event. The first speaker is Igor Kluster from Bocconi University in Milan. He's a fellow of the American Statistics Association. He's a fellow of the International Society for Vision Analysis. He's a fellow of the Institute for Mathematical Statistics. He's the current co-editor of Vision Analysis is also a facilitator of the analysis of statistics, operational research, and econometrics in statistics. His main interests are Bayesian parametrics, Bayesian asymptotics, distribution theory, exchangeability, distribution models, predictive inference. He is one of the most valuable voices in our profession in Bayesian statistics and Bayesian parametrics in particular. Today, he's going to talk about Ferguson's 1973 breakthrough, a timeless inspiration. Even.
Okay, thanks a lot, Michele. Thanks a lot for the invitation. Great honor to be here. It's a great honor to finally meet Professor Ferguson. It's many years that I was waiting for this occasion, and it's finally here. And yeah, it's really wonderful. So what I want to say today is to go a little bit through Ferguson 1973 paper, which according to me, it's really an inspiration, but not just for me, for the whole based on parametrics community. And probably what I'm going to try to say, it's a little bit of personal perspective of how it inspired me, but I'm sure that basically every member of the based on parametrics community will tell a similar story and probably inspirations go in different directions, because it has been really a landmark paper. And yes, so let me start from here. So let me combine Professor Ferguson, who is one of my heroes, with my second hero, who is Bruno De Finetti. And so let me move. Let me also introduce a little bit based on parametrics in the type of framework I'm used to, which is the one Yeah, so let me combine him with my second hero, my two big heroes, the Finetti and Ferguson. And so let me start from really the beginnings. Okay, so essentially what's induction, what's learning from experience. And if I go back to Hume, to the 18th century, essentially to learn from experience, what you need is a symmetry assumption. Okay, so symmetry assumption between past and future. And which Hume also called the principle of uniformity of nature. And the next contribution, important contribution, was to rephrase that notion in a probabilistic framework. Okay? Which, if I phrase it like this, it's exchangeability. It seems a simple concept, but the idea is actually very deep. And it essentially tells you that the order in which the observations come in doesn't matter. Okay? So it's essentially you have a vector of observation, which is invariant with respect to permutation, that leads to exchangeability. Okay? And the crucial point that is also overcomes the independence assumption, which is connected to the classical IIE setup. And so that allows you actually to learn. No? Now I have a dependence between past and future to a probabilistic assumption. And why it's also very important for Bayesian statistics, because we have also the why it's so important? Because of the Finetti's representation, because he introduced the notion of exchangeability combined with the representation. What does the representation theorem tell me? It tells me essentially that every exchangeable law is a mixture of IID laws with mixing measure. Sorry, with mixing measure. Oh wow, that's very. Well, I see. You're right, technological. Okay, with mixing measure, the Q here, which lives on the space of all probability measures, and in the probabilistic literature, it's referred to as the De Finetti measure. If I'm a Bayesian, then it's my prior distribution. Okay, and it's also great from a philosophical point of view, in the sense that it really justifies the Bayesian way of proceeding. So it's not so much anymore likelihood that I put just a prior, which comes out of the blue for my parameters, but to every exchangeable law, there is one and only one prior associated. Okay, so I established that connection, which justifies really the Bayesian wavelengths. Okay, so I want to learn from experience, embedding things in an exchangeable setup, and the exchangeable setup allows me to use the usual base Laplace machinery with my likelihood and my prior. Obviously, then in the non-parametric setup, I don't really have a likelihood, but I have a prior, which lives on the whole space. Obviously, I can express also the kinetic representation. Wow, the kinetic representation here must conditional IID, which is a more customary way of seeing things. So the observations are IID, conditionally on the random variety measure P tilde, and P tilde has a certain prior distribution Q. Okay, so that's the usual Bayesian setup. So let me contrast a little bit parametric versus non-parametric. So if I have my definitive measure Q, which is degenerate now on a subclass of the space of all variety measures, indexed by a finite dimensional parameter. Think, for instance, about the Gaussian distribution, where just the mean and the variance vary. In that case, obviously, it's indexed by a finite dimensional parameter, and the prior Q puts mass 1 on the parametric family. So in that case, I'm back in the parametric world. If that doesn't happen, if there's no way to index things by a finite dimensional parameter, then I'm in the no. Okay, so it's kind of, for the moment, just residually defined. And definitely with this notion of exchangeability, the representation theorem and so on kind of lays the framework for based on parametric treatment, but nothing happened. Nothing happened. And it's interesting that Dennis Lindley actually, in his book in 1972, it's a nice little book on published by Silent. He actually wrote that Dennis Lindley is actually a towering figure which within the UK Bayesian community. So he's essentially the initiator of Bayes in the UK, and he has like the most famous Bayesians in the UK, like Adrian Smith, Tonio Hagan, Bernardo, or Tom Leonard. They're all students of Dennis Lindley. And I just checked today, actually, it has like more than 400 descendants, according to Math Genealogy Project. Okay, so it's really a towering figure in the UK. And he, in 72, he actually wrote that it's perhaps worth stopping to remark that the Bayesian method embraces non-parametric problems, but cannot solve them because the requisite tool is missing. Okay, so the requisite tool, what's the requisite tool? Essentially, I need a random probability measure, okay, a non-parametric one, so whose law is not indexed by a finite dimensional parameter, and I need not just the random probability measure, but I need something which is tractable. What does tractable for us mean? Since we are in a Bayesian setup, it means something for which I'm able to compute conditional distributions, so posterior distribution. And that's precisely, it's interesting that Lindley wrote that in 1972, and in 1973, so 1 year after, so probably the paper was already submitted at the time, Ferguson's breakthrough appeared. Okay, and it coincides, and I like it a lot because the way he expressed the characteristic a non-parametric prior should have. He has these two desirable properties. The first one is that the support, for the moment we just said non-parametric prior is something which is not indexed by a finite dimensional parameter, but that's not enough. We want something which has a large topological support. So ideally, it needs to contain all probability distributions, so that the data generating distribution could be potentially any distribution in the whole space of probability measures. So one is that requirement, the support, and the second one is that the posterior distribution needs to be manageable analytically. So analytical graph. Those are the two requirements, written in a very nice and terse way, and today that's the way people still think, certainly I do. Okay, that's what I want from a non-parametric file. And the breakthrough was with the Dirichlet process, okay, precisely in that paper. So an outline of talk, I'm not sure I will be able to say everything, it's part of it. So we go through a little bit the things which appeared in the 73 paper, but also in combination with the 74 paper, which was an invited paper by the Annals of Statistics following the 73 breakthroughs that kind of combined the papers. So I will first look at the Dirichlet process via finite dimensional distributions, which is the original construction of the basic idea, which was really in line with the time. At the time it was the way you were always constructing stochastic processes, even in the probabilistic literature, was through finite dimensional distributions, and then you go and check consistency conditions. Okay. Then I will look at it as the Dirichlet process as a normalized gamma process, which is the alternative construction provided by Professor Ferguson. Third way to look at it, which is a little bit more in line with the Finetti's point of view, is from a predictive point of view, because was Ferguson in 73 paper, also the predictive distributions of the Dirichlet process actually appear. And then the last part, if I have time, I will also discuss a little bit more recent progress, which is on dependent Dirichlet processes, so going beyond exchangeability to more complex structures of dependence, and also there the Dirichlet process plays a key role, no? And dependent versions of it and beyond. Good, so let me start with the first type of construction via finite dimensional distributions. Okay, so here is just a cut and paste, and many of them, as you will see from Professor Ferguson's paper. And that's the definition, which probably all of you are aware of. So essentially, the idea is you take this finite measure, finite positive measure alpha on the space. You can take actually a Polish space X, we have actually a very general setup. And you say that a Dirichlet process is nothing else than if evaluated on a partition, on a measurable partition, the distribution is a Dirichlet distribution. So according to the Dirichlet distribution, which we all know, and the parameters are given by the measure alpha evaluated on those sets. Okay, so that's a key idea, the fact of using the measure alpha to give the parameters to the Dirichlet distribution. Okay, now it sounds simple, but I mean, coming up with that idea was definitely not. Okay, so using a measure alpha to assign the parameters of all possible finite dimensional distributions associated to a stochastic process, in this case, a random probability measure, which is the Dirichlet process. Okay, so that's the original definition. What about the two desired properties which were laid out? Okay, support, analytical tractability. Well, you can't have much more than that, in the sense that the support of the Dirichlet process is the set of all probability distribution. Okay, in the topology of weak convergence, which is the natural topology on the space of probability measures. Okay, so it has full topological support. So any distribution in the space of probability measure is a candidate data generator. What about analytical tractability? Well, there also you cannot hope to get more than that. But actually, it turns out that the Dirichlet process is really the only one which enjoys such a nice property. It has really not just one analytical tractability, but conjugacy. And conjugacy in a non-parametric setup, we can have different twists of the notion of conjugacy. Here you really have the strongest, in the sense that you have essentially a parametric form. That the posterior distribution is again a Dirichlet process with updated parameters. Okay, so you cannot ask more than that. So you have that the Dirichlet process, a posterior, is conditionally on your data, is again a Dirichlet process with parameter measure alpha plus point masses at the observations. And then if you want to be more sophisticated and use the Dirichlet process, say in a mixture model or on a latent space, then the update will be the parameter measure alpha plus point masses at the latent variables. Okay, so here I'm keeping it simple. So let's say the observations. So more than that, you cannot hope to get. Okay? In other circumstances, what you get is more kind of a structural type of conjugacy, that the prior distribution belongs to a certain class of processes, and the posterior distribution is not the same type, but belongs to the same class. Okay, so it's kind of a weaker versions of conjugacy. But let me also stress that, and that's very important in the paper, it's never stated that what's required is actually conjugacy. Okay, what's required is analytical tractability. Conjugacy is the most you can hope for in terms of analytical tractability, but there's really no conceptual reason why I would want to work with trials which are conjugate. Okay, for me it's enough that they are analytically tractable. Okay, so the Dirichlet process satisfies all these nice things. Another important property of the Dirichlet process, also highlighted by the 73 paper, but also in a companion paper, essentially, because in 73, actually, a lot of fundamental papers on the Dirichlet process and around the Dirichlet process appeared, and this very nice paper by Dirichlet on the discreteness of the Dirichlet process. So the Dirichlet process, even though it has full topological support, its realizations are actually discrete distributions. Okay? And so every realization, you get a discrete distribution with an infinite number of points. So the mass is spread on an infinite number of points with associated certain masses which sum to 1. So these are the probability weights, the random probability. Okay? So that's a realization of a Dirichlet process, and the jargon we use in the Bayesian parametric community, we say it's a discrete non-parametric. Okay, a discrete non-parametric where play a central role in Bayesian parametrics, also because they are really key to clustering problems. Okay, which is kind of, if you want a little bit more modern developments which we have in the last 20 years, the emphasis is a lot about clustering, and there the fact of using a discrete random variety measure, whether in a mixture model or in species sampling, in topic modeling, the clustering behavior is really important. Good. And in general, what happens? So if you assume like a machine learner would say a generative perspective of things, then the way you can generate an exchangeable sample from a discrete non-parametric value is to generate a realization of the Dirichlet process, and then you generate a vector of n exchangeable observations from that realization. Since it is discrete, obviously that realization, the vector of values you generate from the realization of the Dirichlet process will have ties with positive probability. Okay, so we will have ties, with the x stars. And how many of them do we have? It's a random number. It's a random number which I denote by kn, so it's a random variable, but really it's something which plays a key role in Bayesian parametrics. So it's the number of distinct values which are generated from a Dirichlet process. So the observations are kn distinct values with certain frequencies and 1 up to n kn, which obviously have to sum up to n. A good way of thinking about that is, goes back to the nice work of Pittman, is in terms of species sampling, that you see the discrete random variety measure as a model for a species distribution within a population. Okay, it's just a metaphor, so just to help intuition. I mean, then you can apply to whatever you want, but it helps intuition. Okay, so the distinct, the xi stars are the distinct labels of the various species you have in the population, their frequencies, and kn is the total number of distinct species in the system. Okay? Just to help the intuition. Good. So we have the Dirichlet process, which has these nice properties, full support, posterior complete retractor, parametric conjugate, and it selects almost surely discrete distribution. Good, but let me look a little bit closer just to start a little bit of saying how the paper inspired a lot of work. I'll give you one example. Let me have a closer look at the construction. Okay, so the construction, the original construction was by setting up this family of finite dimensional distributions of Dirichlet type. So essentially, here you have, should probably all know this, just a Dirichlet distribution. Okay, so we have a Dirichlet distribution on the n-1, k-1 in this case, dimensional simplex, which has this density. Okay, so that's the Dirichlet distribution. There's a slight generalization which is introduced in the paper, which is useful, but it's defined also when the parameters are equal to C. Okay, that makes things work, but I don't go into that. Okay, and that's the Dirichlet distribution. Just to give you a bit of intuition. No, we all know that if the parameters are all equal and equal to 1, then essentially you have a uniform distribution of the simplex. If the parameters are equal but all bigger than 1, then you have a reverse cap as a distribution of the simplex. Whereas if they are less than 1, then you really have a cap. Okay, with the mass spread out in the corners. Okay? That's how the Dirichlet process looks at the Dirichlet distribution. Two other key properties of the Dirichlet distribution. One is the construction in terms of gamma random variables, that's also very well known, but the point is in the paper, they really highlighted why, because they are crucial. The construction of a Dirichlet distribution in terms of gammas is simply you take gamma random variables with shape parameter alpha j and scale parameter 1, and you define a vector of k random variables by taking each of the gamma random variables divided by this. What you obtain is a Dirichlet distribution with corresponding parameters alpha to alpha k, the ones of the gamma distribution. Good. So keep that construction a little bit in mind. And then the second property was again a cut and paste of the table because it's really modern, also the way it's written. No? It's, I typically give it to my students. One of the first things I tell them to read if they want to know something about basic informatics, go back to the 73 table because it's really something which is very modern, also the way it's written. Okay, the additivity property. Okay, the additivity property is also crucial. Pointed out, the main property is the fact that if you essentially merge classes, right, you just think about the multinomial distribution, you merge classes, what happens is that the distribution stays the same, it's again Dirichlet, and the parameters are the sum of the parameters of the classes you have merged. Okay, so that's the so-called additivity property. And that's crucial. As pointed out in the paper, that's what makes the consistency conditions on the finite dimensional distribution work to show the existence of the Dirichlet process. Okay, so it's all the here. Okay, so the key of the construction is here, the additivity property, right? And with that, you're able to show the consistency conditions. Okay, and obviously from this you obtain immediately that marginally, if you just look at the random probability measure on a single set, what distribution does it have? It has a nice beta distribution with parameter alpha j, and the second parameter is all the others but alpha j. Okay, so that's the additivity property. Those are the two key properties of the Dirichlet distribution, which are used in the construction. So, first inspiration, let me say, okay, let's try to replace the gamma distribution with something else. Can I do that? Do I get, I'm able to construct a different non-parametric prior by replacing the gamma with something else. And so let me try one. Let me try the inverse Gaussian distribution. Okay, the inverse Gaussian distribution, I know, as this density here. And crucially, like the gamma, it's additive in the shape parameters. Okay, what can I do then? I can actually define the so-called normalized inverse Gaussian distribution, where I just do the same operation I did with the gamma random variables to obtain the Dirichlet distribution. In this case, I obtain a new distribution, which is the normalized inverse Gaussian. How does it look like? Well, it's not as nice as the one of the Dirichlet process, so the Dirichlet distribution, but it's still tractable. Okay, you see the density up there. It's in terms of a Bessel function, which is easily computable, and it has actually a different, slightly different type of behaviors with respect to the Dirichlet distribution. Here I just compare it to, in the one-dimensional case to a beta distribution, and you see, for instance, that compared to the beta distribution, when the parameters are less than 1, and the beta distribution goes up to infinity, 0 and 1, the normalized inverse Gaussian goes up to a certain point that I looks like this. And so you actually obtain quite different shapes, the same for positive parameters. Okay, and so we have actually a new distribution on the simplex, just by replacing the gamma with an inverse Gaussian. And crucially, since the inverse Gaussian was additive, also the normalized inverse Gaussian distribution on the simplex is additive. Thanks to this nice additivity property, what I can do, I can actually define a new process exactly in the same way as Ferguson did in his paper. Okay, instead of I just can replace now the Dirichlet distribution with the normalized inverse Gaussian distribution, and the construction carries on. And what I obtain a so-called normalized inverse Gaussian. What about the two desirable properties? Well, I also have them for the normalized inverse Gaussian process in the sense that the support, it has full support. The second one, not as much as for the Dirichlet process. First of all, let me know it's not conjugated. Okay, but I claim, and I will show you later, that actually it's still analytically tractable, even if it's not conjugated. But I postpone that. Okay, so full support, analytical tractability. Let's go back to that. At the point then it's natural. No, we found another example which we can do. And so we have now an alternative non-parametric prior. We can actually compare them. They have quite different type of properties. The point is, can I do that systematically? You know, can I obtain a whole general class of distributions just by doing this replacement? Okay. For instance, just by using instead of a gamma an infinitely divisible distribution normalized by the sum. The point is, unfortunately, not many of them have this additivity property. And without the additivity property, what I obtain is new distributions of the simplex. Yeah, that I get, but I don't get them additive, and so they cannot act as a family of consistent finite dimensional distributions. So, and as far as I know, the only cases for which the resulting distribution, the simplex, then is again additive, so I can use it as the ingredient to construct the new random probability measures, the normalized half-stable process, and another case, which is the normalized superposed gamma process, and that you obtain essentially also taking inspiration from another paper of Ferguson, where he considered what he called the simple homogeneous process. If one of those parameters, you take it an integer, then you obtain that case. Okay, so that's another one which is embedded. And so essentially we have three examples, okay? But still, I mean, it generated quite some nice work in the sense of generalizing the region. But probably it's not the best way, no? Because of that factor that we lack this kind of attitude. So let's go and look at a second construction, again proposed in the 73 paper, the Dirichlet process as a generalized gamma process. Okay? And again, a little bit of cut and paste from the paper. Okay, and here I combine it a little bit also with the 74 paper. So the basic idea is written out essentially there, no? In the 73 paper. The idea is, like I obtained the Dirichlet distribution by normalizing gamma random variables, so I should obtain the Dirichlet process by normalizing a gamma process with independent increments, where there are some, okay? So by the total mass of the gamma. A little bit more formalized in the 74 paper, that it's a Dirichlet process, okay? So the corresponding random cumulative distribution function can be obtained by normalizing the gamma process. Okay? Normalizing gamma process, not really the standard gamma subordinator, but with a time change according to this measure alpha, a finite measure alpha, which is important. Okay, it's the same measure alpha we had before. So essentially, we're out of the usual probabilistic framework where we deal with processes with stationary independence. So this time change breaks the stationary. Okay? And that's kind of a typical thing which happens when you work with objects, processes, random measures, which are important in probability theory. But to make them work for use in based on parameters, actually typically you need to generalize them. Okay? And I will have an example also later of some comment of Professor Ferguson about that. And so here, for instance, it's actually a generalization of the usual notion of the gamma process, so gamma. Okay? But so you can define the Dirichlet process in this different groups, so as a consistent family of finite dimensional Dirichlet distribution, as a normalization of a gamma. The two definitions are equivalent, noted by in the 74 paper. The only thing is that extension of the gamma process to arbitrary spaces is not so well. Yeah, so that's what I think which is noted in the 74. Again, can this alternative construction be generalized? Okay? And idea, can I obtain a whole class of processes, not just cherry picking 1, 2, 3, 4, 5 distributions? And the answer is yes. The answer is yes, and I can generalize it. First of all, I can generalize this to general spaces. I don't have to restrict myself to the real line. And on top of that, I can do it for a whole class, in the sense that I can do it for every process with independent. Or better, to generalize it to abstract spaces, with a completely random measure. Okay, completely random measures are essentially the notion of independent increment on a more general space. Okay? And those were introduced by Kingman in 1967 in a paper in the Pacific Journal of Mathematics. And then they are very nicely treated in his book in 1993, Watson Process by Oxford University Press. So I really recommend that book. And so essentially, what's a completely random measure? It's essentially a random element which takes values in the space of bounded finite measures. What's the space of bounded finite measures? Space of measures where if I evaluate the measure of a finite set, it's fine. Sorry, on a bounded set. And on top of that, the property they have to satisfy is that if I evaluate the random measure on these joint sets, they give rise to independent random variables. So you see the notion of independent increments. Here it's, I'm going to say, think about the plane, for instance. I take these joint sets, I evaluate the measure of these joint sets, gives rise to independent random variables. Okay, so that's the complete random measure. Realizations of a complete random measure, let me assume for the moment it's without, for the moment, or well, actually, you think simple, without drift, without fixed jump points. Okay, they are discrete. They are discrete, remember the Dirichlet is discrete, and so a complete random measure, that's obviously not a random probability. That doesn't sum up to 1. But it's a discrete random measure with random jumps at random locations. Good? That's the complete random measure. And why is a complete random measure so useful? Essentially due to this tool, in the sense that when you work with random measures, you essentially can forget about having a marginal distribution of density. No? In the gamma case, we do have it, but it's an exception. No? The gamma completely random measure. For that one, I know that the gamma random measure value of one set has a gamma density. In general, I don't know that. But what I do know is that to every completely random measure, there is associated one and only one Levin density. So essentially, I have to make this kind of conceptual step and forget about marginal densities and just work everything in terms of the Levin density. And it's still very nice because I characterize completely a completely random measure, which is an infinite dimensional object, by a deterministic measure. Okay, so that's the nice thing. Just the step I need to make, you have to forget about having probability density functions of the measurable values of an set, but I do have the Levin density. And the whole random measure is characterized by that Laplace function, okay, that encodes the whole information about the random measure. Good. How does such a Levin density measure look like? Essentially, it has to satisfy this integrability. So the tail has to be integrable, and near the origin, it's okay to be infinite, but it has to be finite if I help it with a limit. Okay, so it's potentially it has to be infinite. And again, borrowing Ferguson's terminology, which introduced for processes with independent increments on R, we speak about homogeneous completely random measures when the Levin density measure factorizes. What does it mean when it factorizes? It means essentially that my completely random measure has jumps and locations which are independent. So the jump, let's think about the completely random measure just has 10 minutes. No, I have more. So the complete random measure, just think about it. It spreads mass randomly on a space. And saying that the jumps at the location are independent means that if here there is some mass, the mass associated to this particular location is independent of the location itself. Obviously, the non-homogeneous case is the other one where the jump distribution depends on the location. And in most clustering applications, we are happy with this one. In survival analysis applications, we are almost always end up with non-homogeneous, which is something more difficult to deal with. Okay, even if I start in a survival analysis application with something homogeneous, the posterior will be non-homogeneous. Okay, so that's more or less the two situations. Good. Just to give you a few examples of how the Levin density measures look like. Up there you have the one corresponding to the gamma, the sigma stable, and then a little bit, those are the two key ingredients. One is light state, the other one is heavy state, and then the other ones are all a mix of them. Again, one example is the simple homogeneous process introduced in the paper by Ferguson and Fadia in 1979. And regarding completely random measure, because it was also about completely random measures, let me also mention that today the algorithm for sampling a completely random measure, the best way to do it is actually to resort to the paper by Professor Ferguson and Professor Clark in 1972, so 1 year before the 73 paper. Because why that? It allows you essentially to sample a completely random measure. And obviously, since the jumps are infinite, you have to truncate at some point. And the best way to do it is to sample them in decreasing order of the jump size. And that's precisely what Ferguson and Clark did in their representation. and work the name and essentially don't take a neural algorithm. Okay? That's today still the best way of sampling from complete neural networks. Good. Let me go back a second to the idea of the alternative construction. The alternative construction was I take a gamma process, normalize it by its total mass. Well, I can do the same now for completely random measures, in the sense that now I take a completely random measure, make sure it's almost surely finite, make sure it's almost surely positive. Asking that it's almost surely positive means that the jump part of the intensity measure has to be infinite, which means that I need to take completely random measures which jump infinitely often, not just on an unbounded interval, but also on any bounded. So they have infinite number of jumps even on bounded sets. And I can define then a new class of prior distribution given by normalized completely random measures. Okay? Just really taking starting from the 73 papers, that's what you can do. Okay, just using the notion of completely random measure, making sure that you normalize by something which makes sense. Okay, so positive and finite, you obtain a new class of non-parametric variables. And the nice thing is that they are characterized by the intensity measure, so by the deterministic measure. Infinite random, infinite dimensional object characterized by a deterministic measure. Good. Essentially, for those, we always have the support property. The point is, we have a posterior distribution. And let's keep those two. Okay, the two, again, let me go back to the two desired properties spelled out in the 73 paper. Support, fine. Full support for all normalized completely random measures. Are the conjugate, and the normalized inverse Gaussian is actually a special case of this general class. Are the conjugate? No. Okay, and it's a characteristic property, it can characterize the Dirichlet, because the Dirichlet process is part of this family. So the Dirichlet process is the only one for which the posterior distribution is still a normalized distribution. Okay, so it's the only conjugate in there. So should we throw everything away? No. In the sense that they are still analytically tractable. They're analytically tractable in the sense that you work essentially conditionally on the data and on an additional latent variable, let me call this latent variable UN, and then the distribution conditionally on the data and on UN is still a normalized completely random measure. So we don't have conjugacy like in the Dirichlet case, that the posterior is again Dirichlet. But we have that if we condition on something additional, so we have one additional latent variable, it's still conjugate. Here we have the structure of the latent variables. Don't get scared, no? Because here now it's with respect to every completely random measure. Okay, so just note that everything is expressed in terms of what we have for every completely random measure. The Levin test. Okay, and then once you want to deal with a specific one, you just plug in the Levin density measure to obtain what you want. Okay, and that's a posterior characterization, just to show you that it's analytically tractable. And the posterior characterization for these normalized random measures, how does it look like? So it's conditionally on XM, conditionally on UN. Okay, so you have this double conditioning. So it's again a completely random measure plus random jumps at fixed locations. The fixed locations are again the observations, or again in a more complex model, it's the latent variables. Okay. So that's the structure you have, completely random measure plus random jumps at observations, and everything is explicit. The update of the Levin density measure is to an exponential. Okay, so you have the original Levin density with an exponential in front. You have the distribution of the jumps, which are expressed again in terms of the Levin density. You know that the jumps and the completely random measure are mutually independent, and then you have the posterior representation of the random weight measure again as a normalized completely random measure now with fixed points. Okay, so it's analytically tractable. So starting from the Ferguson alternative construction, you really get a nice and wide class, which is of interest because it's obviously general in this case. You have many nice examples, and also it helps obviously the understanding of the Dirichlet process itself. Here just another example, for instance, in this class, if I pick, and that's the closest you can get to something conjugate, if the normalized generalized gamma process, if you start from that, the intensity, what you obtain as a posterior distribution, you obtain a conditional on xn and on un, it's again a generalized gamma, completely non-conventional, with gamma distributed jumps, and then mix over with respect to a certain latent variable un. And so that's extremely simple. How much time do I have? 7 minutes, okay. But let me, those historical remarks, I really want to make them because I think they're important. So the first one, to establish the connection between general independent increment process, by general I mean the whole class of independent increment process, not just a single one, was Doxon with his 1974 papers, or what is it? No, 1974. In the analysis of probability, where he established, where he introduced essentially another class of non-parametric variables, which are called the neutral-derived processes. And he characterizes them, the cumulative distribution function as 1 minus e to the minus an independent increment. Okay? So that was the first time which the connection between base parametrics and general independent increment processes were established. Actually, Ferguson wasn't very aware that independent increment processes or completely random measure were important for base parametrics. And in particular, when he wrote the nice paper with Clark, what he wrote, that there was essentially about a representation, a serious representation of the processes with independent increments. In his nice and terse way of writing, there is at least one application that requires such a generalization, because also there you have to make, with respect to the standard probabilistic way of treating independent increment process, some generalization. And he mentioned that based on parameters is the motivation for doing such a kind of generalization. Another thing I want to say is that most based on parametric models are actually all transformations of or independent increment processes if you want to be on the real line. The Dirichlet process we saw, normalized completely random measures we saw, neutral to the right processes I just mentioned it up there. Other models which are important, it's the cumulative hazard models, which go back to Ms. York, but the modern counterpart is the machine learning model of the Ingham-Buffet process, which is exactly the same thing. Those are all transformations of completely random measures. Mixture hazard, which go back to the nice paper by Dixon and Loud, taken up in generality by James in 2005, or Gibbs trials, which were introduced by Kane and Pittman in 2006. So completely random measures are really kind of the unifying thread of all based on parametric models, a part of the Gaussian process, okay, which is also another big part of based on parametric. Importantly, in the 74 paper, which is kind of the companion paper of the 73 paper, the first posterior representation in the spirit of the one I showed you before about normalized completely random measures was actually given in this paper. Because in that case, it's a bit simpler because you don't need to condition on an additional latent variable, but you obtain actually a posterior representation as an update of the Levin densities plus random jumps of the observation. So you see the structure is exactly the same. So it's really, it was very inspiring for obtaining the general posterior representation for normalized completely random measures. Actually, a combination of those, you can derive a general technique for obtaining posterior distributions for all of those models. Okay. Good. Then at this point, I think I'm essentially out of time. Let me just jump towards the end. So I wanted also to say a little bit about predictive. Sorry. Okay. So I skipped definitely the proof technique, but let me. No, I want to do that. Let's say a couple of words about predictive distributions. Another thing which is inside our paper is the derivation essentially of predictive distribution, or the Bayes estimate, which are exactly the same thing. No? In a Bayes setup, the predictive distribution, for example, with the Bayes estimate, both are the posterior respective. And Ferguson derived them for the Dirichlet process as a linear combination of my prior guess of the shape, okay, which is the probability measure which alpha is composed of, and the empirical measure with weights of the convex linear combination given by the total mass of the parameter alpha. Okay, that's the predictive distributions of the Dirichlet. And are they characterized? And the answer will be yes. Okay, so let me pose this question in general. So assume the observations are exchanged. Assume the prediction rule is a convex linear combination of my private and empirical. And the weights can be anything. Okay, so that's the way I predict. By a convex linear combination of private and empirical measure. And the point is, what is the underlying definition? Okay, so what's the private distribution which corresponds to that system of predictive? And the answer is the Dirichlet. Okay, even without fixing the weights of the convex linear combination. That was essentially proved independently by Gazzini, who was my PhD supervisor in 78. It was always a paper in Italian, so it's obvious that it's independently shown after many years by Albert Lowe, but it was very independent. The weights of the convex linear combination have to be those Dirichlet process and the parametric are associated with distribution. So that's another way of introducing the Dirichlet process. So essentially, if I tell you, my learning mechanism is a convex linear combination of empirical distribution and my variables at the shape of the data, I'm again back in the Dirichlet world. Again, also here, can we do more? Can we do more? Can we do something more? Because here you actually start seeing a little bit of a drawback in certain context of the Dirichlet process. The fact that if P0 is diffuse, then the weight attached to P0 represents actually the probability of generating a new value. Okay? And having the probability of generating a new value, depending just on the sample size and on a parameter, but on nothing else of your sample information, is a little bit restricted. No? It does depend on the sample to the empirical measure. But the first step of predicting, so deciding whether it will be a new value or a value I've already observed, not depending on the sample information, is a bit restricted. No? For instance, if I have all the data in my sample to be distinct, I expect that the following observation will be distinct with high probability. If I have the most of them coinciding, I would expect it to be really low. Okay? Now I have to let me finish this. And so you can do another generalization. Okay, another generalization by looking at that quantity, which is really now, if I go a little bit more in the clustering perspective, that's really the key quantity you should look at for every discrete informative value, the probability of generating something. That you can actually do a characterization, and so introducing in a different way, another way of going beyond the Dirichlet process in this way. So if the probability of something, a new value, depends just on the sample size and nothing else from the data you have, you're the Dirichlet case. The intermediate case, where it depends on the sample size and on the number of distinct values in your sample, but not in the frequencies, that leads to another new class of priors, which are called Gibson, okay? Which are very practical, very nice, because you really specify a learning mechanism. Now I have a learning mechanism in which I assign the next value to new or old cluster according to using the sample size and also the number of distinct values I have. Okay, so that's another way of going beyond, inspired by Professor Ferguson's work. Let me just close with the really last slide. If a lot, somebody is interested, I'm happy to leave the slides. A final remark, which I cut out of the 74 paper, which is extremely modern. No? Well, you can read it, no? The difficulty of putting the cost of computation into the model, no? In a paper 50 years ago, 49 years ago, making that kind of consideration, which we hear nowadays every day, no? Where we are in this kind of trade-off between, as said here, between quick and easy and optimal. No? You have to face it every time. And also, every seminar I give, now I get somebody raises a hand, what about scalability, no? Which seems to be the new mantra. And but almost 50 years ago, is the type of thinking which, considering the computational cost, the position is not unique. And so a few personal thoughts. So I'm asking myself whether the pendulum was recently will swing too much towards quick and easy. My answer would be probably yes. Probably at some point we will go back a little bit. And last but not least, I think that it's only with foundational work like what Ferguson did, which is capable of inspiring new research actions 50 years after the publication that we really move forward. So, thanks a lot. Has been
Thank you. So we are a bit behind. Actually, we were starting late. No. So let's move to the next speaker, Peter Müller, who is a professor of statistics and mathematics in Austin. So Peter is a recognized statistician. He has been working on different fields about statistics and mathematics. He is recognized with multiple honors, including the Grand Medal from the International Society of Visual Analysis. He is a fellow of ISPA and ASA, and the IMS. I'm not going to spend more time just because of the interest of time, but it's really an honor to have Peter here with us.
Thank you. It's an honor to speak here. Well, it's kind of really challenging before this talk. Actually, a complete change of gears. I want to talk here like through some of the application side, like just how useful Professor Ferguson's work has proved in many applications. I tend to work a lot in biostatistics and bioinformatics. In particular, I chose an old paper that just illustrates going beyond the IID case. So I'll talk a little bit through using these models in a situation beyond the IID case. Nothing super difficult or fancy, just an illustration of how it gets used in applications. So I want to talk about using non-parametric base for bivariate current status data. Current status data is simply data that's left and right censored. So all that you get to observe of some event time at a certain observation time, you get to see whether the event has happened or not. Like a patient comes in for a visit, and you can see whether the patient has the symptom, which means time to symptom has occurred, or does not yet have the symptom, which means symptom comes later. It's bivariate. In our case, we have time to infection and time to symptom. So only having current status data means there's really only 4 cases. At the time of the visit, on the left side in those 4 panels, the time of the visit would be the CI on the diagonal. There can only be 4 cases. Either both are right censored, means when the patient comes in, there's neither infection nor symptom, or both are left censored, that's the left lower corner, or the other 2 variations. So it's like precious little information. And to illustrate the challenge with these kind of data, I show you here on the right side simulation study with univariate current status data. In that figure, the dashed black line, that's the truth, it's a survival function. So this is simulated data for event times. The dashed black line is the truth. The green step function is the unrestricted non-parametric MLE. You can see one characteristic thing is you see how you have the huge steps on either extreme of the support of the data. That's typical, like the probability mass piles up on the limits of the data support. And well, it looks ugly being discrete like this. The discreteness you can easily remove by just doing some additional convolution. Then you get something like the blue line is actually with a kernel density estimation. You're still far from the simulation truth. When you start to actually use some dependence with the censoring time, in our case, it makes immediate sense because when the patient experiences a symptom, that's exactly when they tend to come in afterwards. Like when the patient experiences the symptom, they come to the hospital. So you want to assume some dependence between event time and observation time. Then it gets a little better. That is that black curve in between. That is using dependence between observation time, CI, and event time. And then eventually going non-parametric Bayesian, including bioshrinkage, you actually get pretty decent inference here. That's fairly typical. This is joint work with Giorgio Pollon, who is now at Berry Consulting, actually also in Austin, and Gian Carlos Rosas in Lima at Católica University de Peru. Really, I picked this one because I think it's going to illustrate the application of Ferguson 73 way beyond IID sampling. Like, of course, the stylized example is IID sampling, but you can go really far with this. For one, we'll use heavily censored data. Current status data is heavily censored in my mind. We'll have bivariate event times, in our case, infection and symptom. There's actually a third one, like time to visit, but about that third one will be parametric. We'll have a mixture of distributions because there's two scenarios. You can get the symptoms due to the infection of interest, or you can get the symptoms due to some other causes. So we'll see a mixture model there. And last but not least, Igor already mentioned about the dependent Dirichlet process model. We'll have a regression, like rather than just talking about one unknown distribution, like our random quantity is not just one unknown distribution. It's a whole family of unknown distributions indexed with X, where X in this case is implication of covariance. These patients come in with, I think we only have like 3 covariates, sex, age, and treatment. Then there's another variation which we'll not talk much about unless we're left with lots of extra time. There's a nice characterization of these things in terms of tail-free processes, which Igor hinted at one time. So this is the application that motivated this work, data analysis for a clinical study. This is a study that enrolled patients who were treated for gonorrhea or chlamydia. Patients were randomized to treatment or control. The outcome was they observed recurrent infection. And the problem is it was only current status data, means these patients just come back at some time after they're enrolled. And we get to observe whether or not they have infection, whether or not they have the symptom. By only having this one observation, you can simply enroll many more patients. That study enrolled around 2,000 patients, randomized to treatment and control, like the gold standard of clinical trials. Male and female, like mostly female, but still a good number of male, quite a range of ages, and there's around 10% of the patients actually reported an event, which I assume means the symptom in this case. Just to give you some idea of what the data looks like here. And just to highlight again the setup, the context here. So these are patients when they're enrolled after treatment. At that moment, they're disease-free. Then sometimes in the future, they might experience a recurrent infection. And after the infection, they might develop symptoms. And sometimes in between, they come in for a visit. Or another scenario could be they're disease-free when they get enrolled, and then at some time they develop the symptoms, maybe before they get the infection again, because they can get the symptoms due to other causes. So there's really 2 scenarios. You can have the symptoms due to the disease of interest, or you can have the symptoms due to other reasons. We need some minimum notation. I use I to index the patients. The 2 event times here are I sub I for time to infection, S sub I for time to symptoms. The difference is the lag time, if you think of it as the time between infection and symptom. And C sub I is really a first time, but we'll be parametric about it, so we only call it bivariate event time, the visit time when the patient actually comes in for a visit. Being current event, being a current status data, all that we get to observe is whether it's left or right censored. So for each patient, you get to observe an indicator whether infection is left-centered, that's delta I, and an indicator whether symptom is left-centered, delta S. And we know the covariates. So in the end, our data set is for each patient, we have this quadruple of visit time, the two indicators, and covariates. And on the basis of that data, we want to make inference about the unknown time to symptom, time to infection, and make a comparison whether treatment makes a difference in the time to infection. That would be the final inference target. To illustrate the problem here, let's first focus on univariate current status data. So just talking about one event time, say S sub I. It's actually quite easy to show that the unrestricted non-parametric MLE for the unknown event time distribution will be a distribution, will be a discrete distribution with support points at the following locations. Denote with cat A. Cat A here is the, how did you get your fancy pointer, Igor? Oh, it's disabled, I'm not allowed to play. No. Yeah. Sorry. It's scary. It only has 3 buttons, it doesn't get easier, but it's too difficult for me. So let cat A here be the set of all times when we have a left-censored observation following a right-censored observation, means simply a sequence of 0, 1, plus the first observation, plus one more time beyond the last visit time. Then you can easily show that the unrestricted MLE for the unknown event time distribution is a discrete distribution with discrete adjoints probability masses only at the times, let's call them C star in this set. So all that you have to do is optimize over distributing a probability mass over this restricted set. You see here in the picture, can you see I marked all the 0, 1 sequences, and at each 0, 1 sequence you can put a probability mass, and this will be something like this. And on top of that, when you actually carry out that optimization you can do by a relatively easy EM algorithm. It always turns out that the probability mass piles up on either end of the support of the data distribution. You can see that there on the left side, you see the unrestricted MLE. The unrestricted MLE is those green pins. That's the solution to the optimal probability weights at these support points. And that piles up on either end in kind of unreasonable ways. And we can partially mitigate it by convoluting with some kernel. For example, if instead of optimizing over discrete distributions, we take mixtures of normals, you can smooth it out, but you still get that pile up of probability mass on either end. So that's one issue. One way trying to mitigate it is use all the information that you have here. With the current status data, we also get to observe at what time does the patient arrive at the clinic, or in general, the censoring time. If your application allows to make some parameter, if the application allows to make some specific assumptions about the censoring time, I think in our case, we can assume that patients come in when they see symptoms, yeah? Sorry. Patients actually get instructions to come in at a certain time, but most of them don't adhere to the instructions, and they just come in after they see the symptom. Or in general, what we simply assume is that the patient either comes in uniformly over the prescribed time, or an exponential time after experiencing the symptom. So making a particular assumption about the dependence of the observation times and the event times, that obviously can help a lot to regularize it, because that will help you move the probability mass away from either end of the data distribution. And the other thing that of course helps, or always helps, is prior shrinkage. Like such distributions that pile up all probability mass on either end, they're just very implausible. They're like clinically very implausible. It's difficult to argue. And that's exactly back to the title slide. That's exactly what we did here. Dashed again is the simulation truth as a survival function. Green step function, that's the ugly pins that pile up on either side of the data support. The blue survival curve is additional smoothing with convoluting with a normal kernel. We really didn't fix much. Using dependence with the observation times, that helps a lot. That gets you like the gray line in between. And additional shrinkage using a BMP for non-parametric base, not for British National Party. I haven't heard of them for a long time anymore. They disappeared. That really fixes quite a bit in this case. And this is just playing with the univariate distribution. So at this moment, we are ready. You could have let Igor speak quite a bit longer. At this moment, we are ready to move to the bivariate current status data. So there's really 4 cases in terms of the observed pair of indicators for left censoring. Well, we can have 1, 0, we can have 0, 1, and there's 2 more cases. Maybe the 0, 1 is worth a moment to focus on, because 0, 1, that means that infection is right censored and symptom is left censored. That cannot happen when the symptom is due to the infection of interest. So in that case, when you have a 0, 1, then the symptom can only be due to other causes. In all the other cases, the symptom could also, there's 2 scenarios. It could either be a yellow one due to the disease of interest, or it could be due to other causes. In this setup of bivariate current status data in general, you can show that the only items that are identifiable, the likelihood identifiable here, are the CDF of the marginal distributions, like the marginal distribution for infection, marginal distribution of the time to symptom, and these special bivariate quantiles. Those are essentially the squares that I showed you in also on the title slide again. And that is easy to see just by proof by inspection, by staring at the joint likelihood function. You can quickly see that in the likelihood function, all what you really need is you need those 3 quantities. Therefore, any joint distribution of the 2 event times that leaves those 3 quantities unchanged, that doesn't change the likelihood. So it's not like it's only likelihood identifiable up to these 3 quantities. So you cannot learn about the dependence between the 2 event times. That has led people to postulating, for example, copular models. In a copular model, you just write down a parametric form indexed by 1 parameter typically to describe the joint distribution, and the 1 parameter becomes like a sensitivity parameter. There are some papers by Shi and Lewis and Zhu and Prentice that discussed it, and it's being used in many other papers. When you take a Bayesian approach, a natural way to introduce the dependence is by way of introducing frailty. Like you introduce a patient-specific latent parameter, and that drives them both time to infection and time to symptoms, and that way you introduce the dependence. That's a paper by Dunson and Dins. Alternatively, I would argue, especially in this application, there's a lot of structural information we have about these 2 event times. They are not just like there's a meaning to the 2 event times, and we can make a couple of reasonable assumptions. So alternatively, we introduce structure that arises really from the application that will also allow us to learn about the joint distribution of the 2 event times. And that structure includes, in particular, I'll make formal use of the notion that there's really 2 underlying scenarios. It could either be, we could either be in the gray scenario, of the symptom due to other causes. Or we could be in the yellow scenario of the symptom due to the infection of interest. In both cases, I'll write down two different models. For example, in the gray world, if the symptom is due to other causes, then it's reasonable to assume the two event times to be independent in the gray world. In the yellow world, again, if you know that the symptom is due to the infection of interest, then you have informative prior opinions on what the lag time should be, and that's coming up in a moment. In particular, in the yellow scenario of symptom due to infection of interest, we have that order constraint. In the gray scenario, that constraint does not apply. So now we already start to introduce quite a bit of structure in the factors that appeared in the joint likelihood. Remember when we wrote down the joint likelihood, I didn't talk you through the details of how it arises, but I think it's plausible to everyone that you can write down the joint likelihood in terms of these CDFs. There's now already a bit more structure in there. And then we go, this is the same thing, just illustrated again with the same figure as on the title slide, showing you these 4 cases. And then we introduce a bit more structure, and I already gave one of them away. If we have symptoms due to other causes in the gray world, it's reasonable to assume that time to infection and time to symptom are independent. So at this moment, I need the red marginal distribution for time to infection, and the gray distribution for time to symptom when it's not due to the infection of interest. In the yellow world, we'll make another strong assumption. It's a strong assumption, but there simply is bound to be clinical information on that. When the symptom is due to the infection of interest, then there's quite some clinical expertise of how long what should be the delay, what should be the lag time. And you can use that to elicit some parametric family. We just used an exponential, but could have obviously used any other distribution. So at this moment, everything starts to become manageable. And then, there was one more assumption, I should have pointed it out. I assume that in both the gray world and the yellow world, they share the same marginal distribution for time to infection, because we're talking about the same infection. Just the symptom is of a different biologic nature, yeah? And with those additional structural assumptions, you can then actually show that you're getting likelihood identifiability. So now we can actually identify the joint distribution for the bivariate event time. So we are getting down now to, we are left with having put probability models on the unknown marginal distribution for time to infection and the unknown marginal distribution for the gray time to symptom. That is where we use non-parametric base priors. And just to stay away from discrete distributions, we are using the usual convolution with continuous kernels. So we have a convolution with a continuous kernel of some discrete mixing measure, P sub I and P sub S. And for those, we use now exactly the what should actually be known as the Ferguson prior, right? For exactly the reason that Igor so nicely pointed out on the first page, it's analytically tractable and still has like full support. I love to rephrase that full support as non-parametric base is always right in a sense. Like you get the technically well-defined full support of your prior probability model. There we are now. So now we have a reasonably complex inference model for a bivariate status data built with just an ingredient of the underlying Dirichlet process prior. In such a way that in the end, everything actually turns out to be identifiable by creating like a semi-parametric model where they threw in quite a bit of parametric assumptions where you feel comfortable to make such assumptions. Oh, and one more thing comes in. So there was this funny thing that after Professor Ferguson's paper, like for 25 years or so, there was kind of silence, like people recognized it was important, but it was difficult to build on it. And then suddenly it really took off. And then there was another change point, another quantum leap, although quantum leap is the smallest possible change technically, right? But another significant change in non-parametric base, it was end of the 1990s when Steve McEachran came up with a construction for a prior probability model for a whole family of unknown probability measures. Recognizing that our patients come with different baseline characteristics. In particular, one of the important baseline characteristics is treatment assignment. Yeah, if we were to ignore that, then the whole study would be pointless. So patients come with different baseline covariance X sub I, and we certainly want to assume that patients with different baseline covariance have different distributions for their bivariate event times. Less, it would be unethical to carry out that study, right? So we need now a prior probability model not only for a single P sub I, but we need a prior probability model for the entire family, PIX, where X is like our covariance. In our case, it's actually not so bad, the covariance. Two of the covariants are just binary, male, female, and treatment and control. And only the third covariate age is potentially continuous. And that was the ingenious construction that Steve McEachran proposed, where we have exactly the same, sorry, it's again, all what this is really saying is a discrete probability measure with probability mass J sub J and atoms theta J. And what Steve suggested is simply make these atoms theta J, make them dependent across X. They have to be independent across J, independent across the atoms, but they can obviously be dependent across X. And that creates then a prior probability model for that whole family indexed by X. Typical assumption for that theta G of X. So theta G of X becomes now some process indexed by X. Kind of the canonical choice is put a Gaussian process on it. Now, putting a Gaussian process on theta X when the X is just a bivariate binary is a complicated way of saying you're just writing down a linear model, right? And we extend it to H, so there's a little bit of an assumption in there. So if we assume that theta G of X is just X prime beta, all what we have now is the linear weights theta J. Where each of the atoms has like a different straight line. That was the popular dependent Dirichlet process construction. And again, that gave rise to a barrage of literature, like that became a whole cottage industry, people building entire careers on it. In our case, though, when you make the dependent Dirichlet process where the theta G of X is just a linear model, then you could just as well write as the Dirichlet process mixture of linear models, and we come back to that actually. Yeah? Just wanted to point it out as like one way of how the basic Dirichlet process model was taken further to a whole huge class of models that turned out to be super useful in awfully many applications. I already mentioned it before. We make these parametric assumptions for the regression of visit times on the time to symptom. And it's simply reasonable in this application because patients, they will come to the hospital if they get into trouble. And another parametric assumption was the lag time between infection and symptom. And now we have a full inference model, and in principle, we can turn the Bayesian crank. We can turn the Bayesian crank because of the whole thing is analytically highly tractable. Yeah? Like there's a few more details going into it, but many of you can probably imagine how you can implement posterior simulation relatively effortlessly here. So this just shows the posterior inference at the bottom. This is in the end, that's our that's the base rule. It's a posterior mean for the unknown bivariate distribution of time to infection on the horizontal line and time to symptom on the vertical line. And we have pieced it together by our understanding of the application. We have pieced it together as one part coming from the gray world when patients get the symptoms for other reasons, and one part coming from the yellow world when they get the symptom due to the infection of interest. And lest you think this is just prior in and prior out, here would be the same picture under the prior. So the data really informed the inference in this case. This funny discontinuity at the 45-degree line, it simply comes from the constraint under the yellow model. Because if the symptom is due to the infection of interest, it cannot happen before the infection. In the end, we carried out the entire study with the purpose of learning about the efficacy of the treatment. So unless we can quantify the effect of the treatment, the whole study would be pointless and outright unethical to undertake. Although the intervention was pretty harmless in this case, the intervention was just to provide information to the patients and their partners. Now going back to the extension of the Dirichlet process to the some people like to call it density regression, like writing down a probability model for a family of distributions indexed by covariates. You could say that's just a general description of regression. Yeah. I characterized the regression as a dependent Dirichlet process, but I already mentioned at that time, since the nature of the function of the atoms as a function of x was just a linear model, I could just as well take the linear model into the kernel, and then what you get is you just get a Dirichlet process mixture of linear models. The nice thing being that allows me to talk about the mixing measure there. The mixing measure there is a mixing measure P sub I on the linear model coefficients beta J. So it's like the entire vector of regression coefficients. One of those regression coefficients is the regression coefficient for treatment, means that characterizes the difference between patients who are randomized to treatment versus control. And I can now inspect inference on the implied distribution of the effect of treatment, and you can actually show that. So you have something cute to show to clinical collaborators. Actually, for each of the baseline covariates, there was gender, treatment arm, and age. We can actually show the effect of those covariates on the two endpoints, time to infection and time to symptom. And probably the most important one is in the center, the effect of treatment. So treatment is coded with 0 for control and 1 for treatment. Then seeing the time to infection, the density of the linear coefficient of in the TDP model, the linear coefficient for the indicator of treatment is slightly positive. Focus on the center, that's like the 0. And most of the probability mass here is allocated to the right of 0, which means there's certainly evidence for a positive treatment effect, and we could now finesse it and talk about more details. There's evidence for positive effect of age, means younger patients have a shorter time to infection. You can hypothesize for the reasons. There seems to be a negative effect of for women, for time to symptom, etc. And you can talk about all of those. Just again to verify that putting this into this non-boundary base framework really achieved something. Let's look at alternative models. Maybe first at the bottom. At the bottom, this is just a bivariate exponential regression, Gumbel distribution. You really get on top is the inference under the semi-parametric base model that I talked you through. That inference shows you the estimated survival curves for time to infection and time to symptom for 4 different covariate combinations. Don't try to, you don't need to focus on the specifics, just look at the overall shape, and you can see under the bivariate exponential regression, it looks quite different, yeah? So you really capture some additional features there. And going bivariate is also worth it, because the alternative would have been, we could have just separately analyzed time to infection and time to symptom using 2 independent versions of the same model, just for each of the marginals. You're really losing a lot if you do that. So actually making use of the treating it as a bivariate outcome you really learn more, not surprisingly, because we included that rather informative assumption about the regression of time to symptom on time to infection in the yellow world. So you really learn a lot. This is just a little simulation study where on the left top, it shows you the left top is the simulation. Sorry, the simulation truth. The simulation truth are the yellow dots. Like since we simulate the data, we actually get to see the actual event times, although the model only conditions then on the bivariate status indicator. So we get to see the bivariate event times. They are plotted there as the yellow dots, and that essentially tells you the simulation truth. And overlaid, you actually get the inference under the proposed model, which conditions only on the bivariate indicator. Like the statistical inference doesn't get to see the actual data points. You only get to see the indicators. And the reconstruction actually is pretty good there. You can see the simulation truth is obviously, it looks like independent time to infection and time to symptom. And both of them are mixtures. So actually, I think both of them are mixtures of two normals. Yeah. So with two independent mixtures of two normals, we get those 4 local modes. And same for, like on the left top is the gray model, on the right top, this is simulation truth for the yellow model, and down there it's combined, and it does a pretty good job at reconstructing it, almost too good a job. The caveat, of course, is here we simulated data under the assumed structure, but it's perhaps not too unreasonable. We carried out some larger simulation study. Don't want to bore you with the detail, except for what's reported here is integrated mean squared error, I think, for the estimated marginal distribution of time to infection, which is kind of the focus because that's how we define efficacy of the treatment. And there's 3 different approaches in the columns. The proposed one being the last one, and the bold phase means it's doing much better than the other 2 columns. So you really win in large-scale simulation. And there were 3 different scenarios, and many of the scenarios it actually does significantly better without going through all the gory details. And that actually gets me to the end of this discussion. So it's amazing how much structure you can build based on that simple underlying model, starting from really simple assumptions, as Igor beautifully highlighted. And despite and you actually get meaningful, inference with minimal assumptions. We started out with prior probability models on the 2 unknown distributions, the full support, and still in the end, under reasonable scenarios, we can really recover the unknown truth. There's again my favorite line here for BMP in biostatistics. BMP is always right. Yeah. Which is really important because in many inference problems in biostat, if you make parametric assumptions that are just difficult to justify, everything hangs in the air and it's questionable how much you can trust the conclusions. And I leave it at this. Thank you.
So we are pretty behind. I would like to continue with the next speaker, who is Wesley Johnson. He's a professor emeritus at the University of California, Irvine. He has also been recognized in many different ways during his profession, during his career. He's an active fellow of the International Psychology Analysis, of the INS, PSA. He's an active member of ISI, and he's a fellow of the Royal Statistical Society. He was chair of the section of Biostatistical Science of ASA and of
Well, hello. A great pleasure, honor to be here. So I've met Tom a few times along the way. A couple times he gave seminars at UC Davis when I was there. And he came to my seminar at UCI a few years back. We chatted a little bit. And one of the things he said at the time was he'd like to see what other people were doing with this stuff. And so I'll emphasize that a lot at the end of my talk, or towards the end. Yeah, okay. So these are the themes of my presentation. I'll talk about some of my own history. I've known about this paper since the mid-70s when I was in graduate school. And bits from the paper itself, bits about some of students, and bits about the profusion of the work that has been propagated. So I have a lot of references in there. And I see four audiences. One is Tom, one is people here, UCLA local, and BNP people on Zoom. So they know, many of them know a lot more about this than I do. But anyway, I've been doing it for a long time, and of course, I'm one of the members of the audience. So I please myself to some extent in what I present. Yeah. Okay, in 74, 75, I was a first-year PhD student at the University of Minnesota. I'd like to throw in, I loved the graduate education that I got there. Bayesian stuff was taught side by side with everything else. And I guess I've always tried to do that in my own classes since. Don Berry taught a specialty course out of Ferguson's paper and Antoniak's paper, one of Tom's students. It's a follow-up to his paper. I'll talk about that during the lecture. And I just felt like I missed something by not taking that class. And so I was kind of consumed by it, that fact in the beginning of my career. So in '82, I taught a seminar course out of Ferguson's paper. The first big part of the course was just going through all the gory details, and there's lots of gory details. It's somewhat messy in many places. I'll try to dance through that on a slide or two. Anyway, we'll see if I can do it. And anyway, okay, so I also taught a course in survival analysis at the time, and I became very interested in that. And so I became interested in the combination of the two. And then these are key papers that were flowing from Ferguson's 73 paper. One with his student Badia, who's already been mentioned, and another with Prakash Lad and Dick Dykstra. They've also been mentioned already. Anyway, I was enamored of this topic of combining these two things. And so I teamed up with Ron Christensen, who had been in that course. And we were good friends. When I took my first sabbatical at Montana, well, I just went there to visit during my sabbatical. And anyway, beautiful place. But since Ron was an expert in all this stuff, he worked with Don Berry, who had taught that course. And his first paper turned out to be kind of a big paper at the time. And I'll talk about that coming up. So anyway, so I teamed up with him. I was interested in this survival analysis stuff and the Dirichlet, and then we kind of created these papers that are much in the same vein as those on the previous slide. We're just following up in different ways on those things. It's two of the papers are about accelerated failure time. So log time to failure is x beta plus error. You model error in some way as a function of a Dirichlet process. Anyway, so you get a non-parametric, a semi-parametric model. Well, the third paper there, the 89 paper, you see I have an n equals 3 there. The first two papers I have EB, empirical Bayes. We had to do empirical Bayes solutions to them. Well, we got stuck trying to do a fully Bayes solution. And well, why did we get stuck? Well, the third paper shows that with n equals 3, the formulas are absolutely horrendous just to get posterior estimates of the survival curve and so on. And so with n equals 4, I'd probably still be doing some of the calculations. Okay. But anyway, so then with my student Tim Hansen in 2004, he was writing a dissertation with me, and we came back and fixed that up. But it took a long time. So that was the last paper I wrote on Dirichlet processes until 2000 something. And basically I thought, well, this can't be done. If I can't do it I was raised to think everything had to be, you had to have a formula for it. It had to be analytical. We didn't want to be doing anything computational. Well, I guess that was not to be in the end, because everything is computational now. Okay, so anyway, here's a brief version of Ferguson's paper. Goal is to place probability distribution on the space of all probability distributions. Of course, it's easier said than done. I spent 3 weeks teaching that out of that paper. Let P be an arbitrary probability measure defined on subsets of the real numbers. Let C be a collection of well-behaved subset of the collection of all such P's. And so what we'd like to do, what he was doing in his paper, was finding a probability measure script P defined on the set of all probability measures, sigma field, appropriate sigma field, blah, blah. And so that he could, in theory, calculate the script P probability that P is in this set, in this infinite dimensional space. Okay, so anyway, the paper has 6,457 citations. In statistics, that's kind of a big deal. Okay, so, but he establishes this for the particular example where the finite dimensional distributions are here. So one of the nice things about being number 3 is Igor already talked about a bunch of this. So I'm going to be dancing through the same stuff. So maybe second time, if you missed a little bit, will help. And then Peter did more that I was really happy about. Okay, so anyway, let alpha, this is the same notation in the paper, be a finite measure defined on R. A1 up to M is an arbitrary partition of R. Just by definition, let P be such that the vector of probabilities, or P's of all evaluated at all these A's, of the Dirichlet distribution with parameter defined by the alpha measure. Do that for all possible partitions. So also recall, if I look at one set, it's just beta. And the expected value is what I call alpha bar of AI, or AI. And it's just the normalized alpha of A. Okay, this is a probability measure. And such a P defines a stochastic process, indexed by sets. You know, usually stochastic processes we can know as indexed by time. But these are sets. And these are the finite dimensional distributions for that process. All right, so now this is leading up to using the Kolmogorov consistency theorem. And so I'm going to look at the condition C in Ferguson, which is what establishes that, and what Igor actually showed as his I0 in his talk. But I'm doing it for 2 sets. So let B1 and B2 red and black be a partition of R, and then look at a refinement of it. So I got a bunch of red B's that union up to B1, and a bunch of black B's that union up to B2. Well then, P of B1 and B2 has to be distributed the same as the sum of the B's corresponding to each, to the red and the black terms in there, and that's the thing that Igor already mentioned. Okay, so that's condition C. It's a basic property of Dirichlet distributions. And we call P, such a P, or Ferguson calls a P, or a random probability measure, providing condition C holds in it. The A is like a probability measure, so that the P of A's have to be positive and less than 1, and the probability of the R has to be 1 with probability 1. I'm good. My mouth has got it. Yeah, that's why I brought it. Should put it on the table. Okay. All right, so Kolmogorov consistency. Well, Igor mentioned that as well, and this condition C implies it, but what does it mean? So, and in 2 dimensions, I have a P of A1, and we know that has a beta distribution because it's one of the finite dimensional distributions. And I have P of A1 and A2. Well, A1 and A2 are not a partition. Okay, but you can use the finite dimensional distributions to obtain the actual induced distribution P of A1 and P of A2, and then you can obtain the marginal for it. And it's an undergraduate exercise to do that in 2 dimensions. In many dimensions, it's really ugly, but it has to be done. But anyway, it turns out that the marginal of P of A1 obtained from the joint for the red is exactly the same. And so that's what consistency means in 2 dimensions in any case. So anyway, so the Kolmogorov theorem says now there exists a script P defined on this big space with a sigma field, everything all well defined in Ferguson's paper. And so now we have, and it has the same finite dimensional distributions, the Dirichlet distribution. So this thing really exists. So this is really a big deal. You know, anybody can sit down and write down, well, I've got this P and it satisfies this, and then let's go play with it. Well, you'd like to know that at the end of the day, you're going to obey probability laws, and this establishes that. Okay, so we say P is distributed Dirichlet process alpha. Alpha is the parameter of the process. We also say P is a Dirichlet process, and that script P governs P. So it's simple to explain, hard to get. Okay, samples from the Dirichlet process. Well, let X given P be distributed P be distributed Dirichlet process. Well, then you can obtain the marginal probability that this sample from the Dirichlet process is in A. Well, iterated expectation given P of A. Well, probability X is in A has to be P of A, so it's just the expected value of P of A. And so, well, that's the normalized alpha, which I've been calling alpha bar. Okay, so the marginal X is distributed according to this thing. This involves the parameter of the process. Okay, so now the next thing, what's the next thing you want? Okay, so this is the hard part. You want to get the posterior distribution P given X equals X. You want to make inferences about P. That's, I guess, nominally the point at the moment. So as a Bayesian, you got to get this posterior distribution. Well, how do you get that? Well, this is kind of what Lindley was talking about, I think, where something's missing in order to do the non-parametrics. Well, what's the tool that you need? It's the radon from probability theory. Beautiful, beautiful theorem. And it has saved me on a number of occasions where I had no idea what to do until I thought, oh, well, if I look at it that way, that's how I'm going to find this conditional distribution. It's not like writing down likelihood and prior. It takes you beyond that, and that's what makes all this possible. So anyway, that's a kind of a painful calculation. But then once you've done it for 1, you can do it for n. And Igor already mentioned this. So by induction, there you are. All right. So now predictive distribution. Igor talked about that. Well, okay, it's the same thing, slightly different notation. So if I have xn plus 1, a future observation, after I've already observed n observations, well, basically the assumption up there at the top says these guys are all IIDP if I know. And so now I want the predictive distribution. The probability that the n plus first observation is in the set A given the first n. Well, anyway, it's the normalized new alpha corresponding to the Dirichlet process. This one up here. That guy. That's the new Dirichlet process. This is the next observation after that. And so we normalize that. That ends up being a weighted average of alpha bar of A and the empirical distribution. Igor wrote this down already in a slightly different notation. So note, all right, you already talked about this too, but I'm laying it out, spelling it out, which I really like to do. Probability that xn plus 1 equals one of the previous observations that were already there. You just plug into the above one. Plug in xj for A up here. Right there. Well, what's alpha bar of xj? Well, this thing is going to be a continuous distribution. Probability 0 on points. Goes away. And so I'm left with that. And it's positive. So the probability that I see a new observation that equals one of the old observations is positive. Okay. Well, even more interesting than that, and you were already referring to it, the realizations of the Dirichlet process are going to be discrete distributions, and that becomes, it's more obvious, this kind of gets at it, but it's even more obvious when you look at the Seth-Raman construction, that stick-breaking construction that we were already talking about. Okay, so proposition 3 in Ferguson shows that there's positive probability that the Dirichlet process probabilities on sets, arbitrary sets, will be within epsilon of some continuous distribution, any continuous distribution that you pick. So in a sense, it's giving somehow, showing that there's close, the support is, continuous distributions are somehow support, close, what did I say? Somehow close to the support of the Dirichlet. Okay. So it makes things sound better than that you're getting these discrete things when you maybe really want to model continuous distributions. Okay, so then the second paper that Igor also talked about was the 74 paper that he was invited to present. They asked him to provide examples of probability constructions. Well, they already knew about the Dirichlet process, and so he talked about that, and then he also talked about the poetry and some others, and Igor talked about more. But anyway, I fell in love with the poetry at some stage in my career through my student Tim Hansen, who was writing a thesis trying to handle the survival analysis problem, the survival analysis problem that I talked about earlier. And anyway, so he fell into poetries, and so I just mentioned poetries, and these are a few people, there's lots of people working on those guys, but they are competitors in a sense. Not everybody loves them, but I do. Okay, so now Antoniak's mixture of Dirichlet processes. Okay, so you generalize the Dirichlet process. So you have an auxiliary variable theta, and you model P given theta to be Dirichlet process with parameter alpha sub theta. So this alpha sub theta is giving you maybe a parametric distribution as a prior guess for your distribution that you're modeling. So this is somehow making a little more sense if you're trying to make it an inference about a distribution. It'd be nice in statistics anyway to have a family of distributions as opposed to just a single distribution that you're trying to test. Okay, and so this alpha theta could be normal mu sigma squared. Normal mu sigma squared. And then we have we put a distribution on theta, which I'm calling mu sigma squared here, which is simple. So expected value of this P given theta is E of theta, that normal distribution. Well, okay, so then makes more sense, like as I already said a little bit ago. And then and the P specifies this normal family. And well, what's that do? So a special case of this whole thing is going to be that normal distribution or any one of the normal distributions that's possible. But then the Dirichlet process gives you a much broader family of distributions that goes away from that normal distribution. So anyway, this is the kind of thing I think that really makes sense when you're doing statistical modeling, is to have families of distributions to center these non-parametric priors on. Okay, downside, the MDP is an MDP, analytically messy, which I will talk about. It's the this accelerated failure time model that I talked about earlier that we handled with n equals 3 observations. That posterior is an MDP. These guys are messy. Okay, they're not analytically tractable, really. There are a few observations, but it's failing. Igor's forget who you were. Oh, Ferguson, of course. We're out. All right. All right. So there are and another fact that shows up if you're in the survival analysis. You're dealing with censored data. Well, and if you have X given P P distributed Dirichlet process, P given X is in a set. Well, that's an MDP. So sensor data problems are kind of out the window for analytical inferences. Yeah. Okay, so all started with Don Berry and his class. I'm I'm walking by the classroom. There they are doing this thing that I should be in. Okay, and that's my friend Ron Christensen and one of Don Berry's students. They published this Annals paper. It was his master's project. Anyway, so the problem is the classical empirical based problem. That's what Don had him doing. So binomial data, different thetas. Model the thetas as IID from the Dirichlet process. And yeah, and then, well, anyway, you get the posterior of P given X. It's a complicated mixture. It's beautiful. It's a beautiful mathematical result. But anyway, major complexity, there's ties in these data that cause all kinds of problems with writing things down at the end. There's hyperplanes. You have to deal with every hyperplane where these different ties result in different configurations. Clusters, as it were, which clustering is a good thing, Igor talked about, but it's a bad thing here. All right, I like to mention my friend John Dealey and Dennis was a friend too. They wrote a paper called Bayesian empirical Bayesian, fully Bayesian parametric solution to this problem. Okay, what's cool about this? Well, I love the fact that Lumi said there's nothing less Bayesian than empirical Bayesian. So anyway, I always kind of had that ill feeling about it, even though I've used empirical Bayes in different settings in my own work. All right, so these are more of Don Berry's students that have contributed to this whole literature. There's Frank Samaniego. Frank was Tom's student here in the 60s, in the late 60s. He went to UC Davis. This is a picture from the 60s, by the way. Anyway, he was my mentor at UC Davis. I'm pretty sure he's the one that invited Tom to come and give talks there. So there you go. And then he wrote a couple papers with his students using Dirichlet processes in the competing risks problem, which has notorious lack of identifiability problems. Okay, and so they claim that putting a bivariate, putting a Dirichlet process in the bivariate survival function mitigated against those issues. I'm sure there's lots of subtle things that come out of that I'm not prepared to talk about here, but anyway. And then there's Antonia. I was looking for pictures of lots of people, and well, he was one of them, and unfortunately I found his obituary from last year. So I found out that he worked in the Navy before UCLA, went to Berkeley after UCLA, and then he went to Bell Labs. And I think he published more papers in other areas than statistics. But anyway, and then there's Lynn Kuo, the pictures on the next slide, working with Gelfand and Bonnie Malik. And this paper, keep hitting me along, but okay, that is the first numerical approach to handling that problem that killed us off with the accelerated failure timeline. Okay, and there she is. And you can tell by looking at the computer monitor that this is the 80s. She visited UC Davis for a year. Fantastic cook. 5 courses. And you can't believe that there's still another one after you've had the third. You can't believe. Okay, and then there's Alan and Bonnie. They were the co-authors on the previous slide. Okay, and then, okay, so bad things. Well, we already know that the Dirichlet process is discrete with probability 1. That's kind of bad. It was anyway, until we get to the next slide. But anyway, they concocted a situation where trying to estimate a mean using a model that has Dirichlet processes in it, and they got an inconsistent estimator. Okay, well, big deal, because the Dirichlet process mixture comes along, and you use the Dirichlet process to mix parametric distributions. And so mixtures of parametric distributions are kind of a good thing. They smooth things. And well, anyway, that's what's going on here. There's x given theta, parametric distribution, theta given p, theta distributed as p, and then p distributed as Dirichlet process, and that's p is governed by this script p that we've been talking about, and that's the other way we write this kind of model. It's a, what is it? This p is a Dirichlet process. It's a Dirichlet process mixture of parametric distributions, p, p, m. The other one was an MDP, mixture of Dirichlet processes, integrating the integrand in the Dirichlet mixture of Dirichlet processes was apparent. It was parametric. Okay, these guys have beautiful properties. Boom. Lots of hard work in there. There's certainly tons more, but these papers stand out. Estimate of the density. It's the predictive density or an estimate of the density. Either way you want to look at it. For these data, this is the famous galaxy data, which are speeds of galaxies. And this is probably in Peter's and others' book. Peter Fernando, Tim Hansen, and Alejandro Haro have a book. Anyway, and this is probably before that, but it's got to be in their book. So it's the picture of seeing the world around. Anyway, it's a lovely picture. All right, Sephiron construction. Well, this is called stick breaking now. Igor mentioned it a bunch, and this is the first one. I know it anyway. And well, anyway. It's attaching point masses. It's a weighted average of point masses. So the point masses are coming from alpha bar, and the p's, well, they're coming from these beta distributions constructed in this way, so that they'll add up to 1. And well, anyway, they're the right ones. So if you were to sample a bunch of alpha thetas from alpha bar, you could sample an infinite number, and then if you could just construct all these guys, well, and then write P of A, well, that thing's going to have a beta distribution. That thing is going to have a beta distribution, and you have a finite collection of sets that form a partition. Well, that's going to have a Dirichlet distribution. Evaluating this thing at all those sets, creating a vector. Beautiful. I taught this, the proof of this in one of my classes. I've never been so awed in my life by the brilliance of this guy, Sephiron. Anyway, just how in the world he came up with that, I'll never. But anyway, such a beautiful thing, and it's this construction that really has set the world on fire with the Dirichlet process, I think. And then they've expanded it, of course, because you can look at all kinds of other distributions, other ways to construct things like this. And Igor has done a bunch of that. Okay, and so then the Dirichlet process mixture. So you mix, well, here it is. Here it is. This is the expression of that, but that is easy to work with, I guess, in the end. Because of this. So stick breaking, the world on stick breaking fire. Okay, how do you compute this thing? Well, geez, these guys, starting with Escobar, came up with ways to improve upon each other over and over. And Peter's sitting right there, and well, anyway, I think Escobar started it. Neil kind of, I talk about algorithm number 8 for some time. Everybody was using algorithm number 8. It's like love potion number 9. And then there's a more recent one, which involves things that are deterministic, blind, or variational inference. I see a lot of papers using that name. Okay, and then there's more. So those papers, I got to go back a second. No, go back. No, wrong one. Oh, I'm still going the wrong way. You're going to tell me I have to quit. Oh, I was wrong. You'll have to do. Okay. Those first 6 involve polyurban schemes. Okay. Intimately related to all this Blackwell and McQueen, which has been mentioned. So they're marginalizing of the Dirichlet. So that makes life easy. They can make point inferences, they can get density estimates. They can't get estimates of quantiles or distributions. So these guys make it possible to get quantile. And then the Ishwan James is more general. It's not just Dirichlet processes. It goes beyond. And then this is a lovely way to approximate a Dirichlet process. See that it's a finite sum. The theta h's are being sampled from alpha bar. The pH's are coming from this Dirichlet distribution. Who would have ever guessed that with large K was going to be an approximation to a Dirichlet process? So you can do Dirichlet processes in Windows. Or okay, so now how much time do I have? Well, 11 minutes. So I can sit down, relax. Okay.
Okay.
Most of my slides at the end are just, here's a bunch of cool papers in this. Here's a bunch of cool papers in there. So I'm almost done with anything to think about. All right, so there's that accelerated failure time model that I was talking about from those first slides. And well, log T is X beta plus W is distributed parametrically. Beta distributed P, and then so then P is distributed as a Dirichlet process. So what's that? That's a Dirichlet process mixture for the error distribution. So Lynn and Bonnie were the first ones to handle this problem that I'm aware of after we got stuck and quit working on it for 15 years or whatever it was. And well, anyway, they constructed a gibbs sampler. They had to use some of the methods that were developed right up to Neil algorithm. Well, Neil algorithm 8, I think, wasn't there yet. So they were using Peter and Steve's algorithms, or maybe even Escobar. Okay. So I'm 75 years old. This is what happens. It's one of the things that happens. Like looking for the word, and then I finally get it sometimes. Okay. Okay, then there's Kodas and Gelfand. I met him in 1999 in Reading at a BNP conference. And I've known Alan for at least that long. But anyway, so they have a method of handling this same model. They're looking, they want to do median regression. So they have to have a distribution on the errors that has median 0. And they have to fiddle a bit. They have to fiddle a bit, thank you, to make that happen. And then Hansen in his thesis, he came up with this, found the polyetry and started using mixtures of polyetries, easy to get median 0 out of a mixture of all your trees on an area distribution. So anyway, so those guys compete with each other. And then there's Hansen and Johnson, JCGS. Anyway, this is a real fully Bayesian solution to the problem, the n=3 problem that I mentioned earlier that we got stuck. So you can compute. It's a beautiful paper because, well, he constructed his own Gibbs sampler. He didn't have these other guys to rely on. It was a different way, a different kind of model. So anyway, it showed the stationarity of the distribution and that it had the right target distribution, etc. Okay. All right. Longitudinal, these are applications. Okay, and these three at the top, well, they're all handling Dirichlet processes involved with the random effects in a longitudinal model. And for many years, people were using regular old mixed models, and we're handling longitudinal. And anyway, then Fernando, Quintana, and I got together and got a hold of this model. Got a hold of this model. Okay, Taylor, Cumberland, and Sy, UCLA at the time. These guys were all at UCLA at the time. And I call it the model that has everything but the kitchen sink. So it's got fixed effects, it's got trends, it's got random effects, it's got an Ornstein-Uhlenbeck process to model longitudinal correlation. Nice thing about the Ornstein-Uhlenbeck process is it only has a couple of parameters. And so, well, our contribution was to put a Dirichlet process mixture on those parameters. So we have a Dirichlet process mixture of Ornstein-Uhlenbeck processes, which generalizes the correlation structure. I used to love to give talks at the board, and I used to love to break chalk. I wanted that chalk to fly, and so that's kind of what I'm doing now with my hands. Okay. All right. Anyway, and then there's more there. There's Michele right there, and Peter. Bayesian discovery procedure, and one with my colleague Blavak. Different kind of problem. Dirichlet process is making a big difference all the way. Okay. And then there's non-linear model classification from my colleague again. And then these are all back. Yeah, there you go. That was it. Okay, so flexible models for ROC and risk analysis with or without a gold standard. So anyway, there's a lot of papers in there like that. The binormal model for ROC curves is dead, I hope. It could be. Very constricted, very constrained. These guys allow for a lot more flexibility on having normal distributions for the diseased and non-diseased populations when you're trying to come up with an ROC receiver operating characteristic. All right, and then there's the dependent Dirichlet process. Oh, Peter saved me on this. Well, I was planning, I knew I was going to run out of time, and I just thought, well, I'm not going to write all that stuff down that Peter wrote down, but he did. He wrote it all down. You've already seen everything I would have liked on that, except I'm going to tell you the things that people have done. But anyway, you're putting a prior on a collection of distributions, and you want the marginals to be Dirichlet processes. Uh-oh. Okay. Well, could have gone better.
Going just fine.
Anyway, so okay, so you want to correlate those distributions, and Peter told you how Steve did it. Brilliant idea. to have a multivariate distribution on the point masses. One coordinate for each of the distributions you want to correlate. So, and anyway, so here's follow-ups. A more recent one here. I just found out about this one. The science last year, so that would be a cool one to go find out about this stuff. And okay, well, this was McCackern. It's a Dirichlet process mixture. Well, in this case, it's a simplification of the original way that he expressed it, but it's a Dirichlet, and Peter wrote this down, Dirichlet process mixture of linear models. Dirichlet process mixture of linear models. It's a DDP. And, well, okay, so here's an example. So Peter and Gary and I and Maria Gary Rosner. Gary Rosner's data. It's survival data. These are survival estimates of survival curves. There's a low dose treatment and a high dose treatment. And they wondered whether the high dose treatment was going to hurt too many people, or if it wasn't going to save more people in the end. Well, anyway, proportional hazard model says those curves can't cross. I taught survival analysis for many years. People wanted to always model their data with the Cox model. Drove me crazy. Well, anyway, here's the answer to an answer to that. And anyway, basically, this says that at the beginning of time, in the early part after being treated, the low dose has better survival prospects. The higher the curve, the better off you are. And so the high dose is killing off more people in the beginning, but then later on, it switches around. So it's not a proportional hazard model anyway, and it says something about that it's more dangerous for some people in the beginning to be on the high dose. Yeah. All right, and then now, Steve also did this in his original paper, but he let these weights depend on X, depend on the covariates in this regression problem. And the goal here for a bunch of papers, the ones that I'm listing there, is to allow for shape of the curve to depend on X. Okay. Well, here's a constructed example by Alejandro Jara and Tim Hansen. And they used a simulation constructed by David Dunson in one of his papers. Here, what? Mike. Okay. Okay. Anyway, here is these are dynamic pictures for different axes, and for the left side is the linear DBP, the right side is the weighted DBP, as in Conley and Mueller and etc. Okay, there's a different X, a different X. Okay, just the shape of the curve is changing dramatically with different X's. So Dunson's true curve is the red, okay? And the estimate is the black, and the dashed. Oh. I keep thinking if I hit it to the left, it's going to go to the left. It just doesn't. There we go. Okay. All right. So true is red. Estimate is black. 95% intervals are dashed. Oh, okay. I thought that was just such the coolest collage. All right. I'm almost done. Really. Spatial data. These are the guys that figured out how to apply to, I think, LDPPs or DBPs anyway. And one of them sitting right here. The model spatial data. And then there's extensions of the DBP, hierarchical Dirichlet process, and the nested Dirichlet process. One thing I thought was pretty interesting. I looked forever to find the number of references to this paper. I could not find it. Well, here's a paper with the same name in it, the same authors, different time, 5,200 citations. How was that? Well, Ferguson did better, but anyway. I think that Google drowns out that paper because of that. Okay, and then here's the books. Some theoretical, there's some in chapters of books. There's the first really good book on Bayesian statistics. I don't know about that, but I think it certainly is the most popular. And then there's one that we wrote. These guys have chapters on parametrics. And then there's this wonderful collage of all of the stuff that we're all talking about in one place in this book. And then theoretical fundamentals, foundations, and then another. Now this is a book in progress on ROC curves. Estimation, it has 3 chapters that spell out Dirichlet process and foliage tree for estimating curves, ROC curves. And finally, thanks to my students, who all these 3 and were involved. I trained them in Bayesian nonparametrics, and that was a real pleasure to do. And then I have all these other guys, and a lot of people know who a lot of these people are. But anyway, thank you to you guys, and that's it.
Thank you. I'd like to leave a very supposed to do. Thank all the speakers for the nice talk. So I'm glad to return that Tom will say a few words to conclude the session.
Mentioned some lots of luck in my life, and one who was when I was born in 1929. Stock market crash created a lot of problems. I went to high school and wondered where to go, and it was the nearest college, but happened to be Berkeley. That was my first great stroke of luck. It was a good college, and I worked my way up. And when I graduated, I thought I might go on in what field, and my father was an actuary, and I thought I'd like to do that. But I looked at actuarial work and I said, oh, didn't know it. And the nearest thing was statistics, I thought. So there, a very lucky thing. I went into statistics in graduate school. And there I met some people other than, well, of course, there was Georgie Name. Very important influence on my life, but 2 other people had even greater influence. One was Lucien Lecoq, the most outstanding mathematician that I knew. He seemed to know everything. And the other was David Blackwell. These 2 things I really feel so lucky to meet them. And always impressed by these people. What we mentioned. Blackwell is the introduction to my paper that suggested the problem to begin with. Anyway, I guess that's all I have to say.
Okay, thank you everybody for coming. So this concludes our special seminar. Okay. There's another reception for the department anniversary. If you have RBSP, you will welcome to stay here. Okay. Thank you.